Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of Electronics and Communication Engineering at MLR Institute of Technology. Today's topic is interrupts. This video is a part of the series Microprocessors and Microcontrollers. If anyone want to know what is microprocessor and what are the basics of microprocessor, please do watch the previous videos. So today's topic is interrupts. So, and the overview of today's topic is what are the interrupts present in 8086 and how the structure of interrupts has been in the 8086 and what is a vector table, how vector table is stored in the memory and what is interrupt service routine. So, coming to the topics here, interrupts. What is an interrupt? As all you know that interrupt is a disturbance occurred for the program or within the program or by the external devices. So, interrupts can occur in many ways. One of the best example of interrupts is if we are taking prints from the printer, at some point of time we have gave 100 pages to print, but we kept only 50 pages, 50 A4 sheets. But here the problem is after 50 pages, the printer throws one exception or one interrupt that out of pages. So it causes that is an interrupt. So interrupt is a disturbance occurred for the microprocessor while executing the program. Temporary halt. Here the microprocessor responds to the interrupt with an ISR, interrupt service routine. So what is interrupt service routine? Interrupt service routine is the program how the microprocessor will accept the interrupt or how it access the interrupts, how it will handle the interrupt. So coming to the types of interrupts. In 8086, there are two types of interrupts. One is hardware interrupts and other one is software interrupts. The hardware interrupts are the interrupts occurred by the external devices, like what are the peripheral devices, what we are connecting to the processor. If that causes an interrupt, then such type of interrupts is considered as an hardware interrupts. And software interrupts. These software interrupts are the instructions given to perform some sort of applications, like to halt the program or to jump the program. So, like in such cases, the software interrupts has been implemented by the programmer into the programs. So coming to the hardware interrupts, here we are having two hardware interrupt pins. One is NMI, non-maskable interrupt, and here maskable interrupt pin is enabled during INTR, interrupt request. As you all see the previous video, like pin configuration or signal description of 8086, at that particular point of time, I have explained what is INTR pin and what is NMI pin. In the concept of interrupts, I will explain here also. So coming to the hardware interrupts, we are having two pins, NMI pin and INTR pin. Here, NMI is non-maskable interrupt. So non-maskable interrupt is a single interrupt in the microprocessor having highest priority when compared to the other all interrupts like software interrupts or other interrupts. Non-maskable interrupt is the highest priority because when the non-maskable interrupt is occurred in the microprocessor need to access that interrupt. It doesn't want to choose whether it will accept or not accept. No, in particular case of NMI, it should accept the interrupt. And how it will activate this NMI interrupt? These are the steps how this NMI interrupt will be accessed by the microprocessor. If the microprocessor some sort of instruction like instruction N is executing, after every execution of every instruction, the last clock cycle, as you all know that we are having T4 clock cycles to complete one execution of one instruction. Here the first clock cycle, most of the times address will be accessed, and in the last clock cycle, the microprocessor will always check whether it is having any interrupts or interrupt request or any other interrupts. At that particular time, if NMI pin is enabled, the microprocessor will complete the execution of that particular instruction, and then it jumps to that particular interrupt, which interrupt it has been accessing. Like in this case, if NMI is accessing, so non-maskable interrupt occur while executing any instruction, then the microprocessor first completes the current instruction execution, and then it pushes the flag register values onto the stack. Why it have to push the flag register? So if any program is performing, the intermediate values and the status of flag is very important for the further execution of the program. So it must be stored in somewhere. So to analyze, to store that particular flag registers and code segment and instruction pointer. So these values are very important to perform the execution of next instructions. So for that purpose, the microprocessor will save this flag register values and code segment values after that instruction pointer values. These values should be saved to perform the next instruction after interrupt. So these values will be dumped into the stack. Intermediate values will always be stored in stack. Then the IP is loaded from the contents of load location, this 0008. It is the location of this particular NMI interrupt. So every interrupt will have some particular location where these all addresses particular. See, if for NMI one interrupt one address location will be there at particular location, is having IP, instruction pointer address or CS address to particularly enable that to execute that particular interrupt. So it will be loaded, IP will be loaded from that particular contents and CS will be loaded from that particular contents. After then it will execute the interrupt, NMI interrupt. So okay, interrupt has been completed, interrupt is done. Then it need to execute the instruction n+1, next instruction. So it will jump to that particular interrupt location, it will execute the interrupt unless it has been fetching the instruction I written. So it should have every interrupt program will end with this I written instruction written from the interrupt. So when this instruction is encountered by the microprocessor, it will execute, it will come back to that particular next instruction which in the main program. So in this particular sort of execution, the process how this microprocessor is enabling the interrupt, how it is getting back to the main program is nothing but interrupt service routine. Interrupt service routine. This is all about the NMI pins. So when coming to the next hardware interrupt pin, which is nothing but INTR. So this is the maskable interrupt. Like it can, whether the microprocessor can accept the interrupt request or it can deny the interrupt request. So how microprocessor will say whether it is accepting the request or denying the request? It will acknowledge to the other peripheral devices by using INTA, interrupt acknowledgement pin. So INTA pin is the acknowledgement given by the microprocessor whether it is accepting the interrupt request or denying. So which are the conditions that microprocessor will accept the request of an interrupt or it will deny? So if the microprocessor is having the interrupt request from the other peripheral devices, first it will check the IF, interrupt flag, in the flag register of 8086. So if the microprocessor is getting INTR request and at that particular time if IF, interrupt flag, is equals to 1, then so it is enabled. So INTR is enabled and IF is enabled, interrupt flag is enabled, then the microprocessor need to enter into the mode that it should accept the interrupt. It will perform the interrupt. If the interrupt request is there, INTR is there, but IF is equals to 0, interrupt flag is disabled, then the microprocessor will not entertain the interrupt, it will execute the normal main program itself. Okay, if INTR is enabled and IF is also enabled, if for this both condition, the microprocessor need to accept the interrupt and it need to perform the interrupt request. So how this interrupt request will be accessed in the case of INTR? So these are the actions taken by the microprocessor to perform the interrupt request. So first it completes the current execution as same in the NMI. It activates INTA output that it receives some type of instruction and it need to perform that particular interrupt. Then the same will be performed, like it will store flag register, CS value, IP values into the stack. Now IP value and CS value will loaded with that particular interrupt address. So there is a doubt generated that you are always saying that IP and CS will be loaded with the address of that particular interrupt. Where these addresses will be stored? So all the interrupts which we are having as 256 interrupts will be accessed by the software interrupts in the 8086. Or for these 256 interrupts, the address of every interrupt, IP and CS address of each interrupt will be stored in one memory location. It is nothing but the interrupt vector table. Interrupt vector table. So these 256 interrupts addresses, IP addresses and code segment addresses will be stored in one memory location, which is nothing but the interrupt vector table. So interrupt vector table, this particular microprocessor will get IP and CS value of that particular interrupt which is stored in the interrupt vector table, and after completing the interrupt execution, the interrupt flag and trap flag will be set to 0 condition. It will be disabled. So these two are regarding these two instructions, NMI and INTR, regarding the hardware interrupts of the 8086. While coming to the software interrupts, there, as I already told you, that we are having 256 interrupts in 256 software interrupts in 8086. Here the interrupts of software interrupts of 8086 will be accessed by the mnemonic INT interrupt, and here type, which type, like as I already told you that we are having 256 software interrupts which can be addressed by using 002FF. These are the hexadecimal representations of the interrupts. So it is 2-byte instruction. Int is 1 byte, and the specific type which interrupt has been accessed by the microprocessor. So out of this, the instruction is of 2-byte instruction. The first byte provides the opcore int and the second byte provides the interrupt type number here. So for execution, the starting address of type 0 interrupt. So as we all know that we are having 1 MB. Microprocessor 8086 can support 1 MB of memory. Out of this 1 MB of memory, the first kilobyte of memory is reserved to store the interrupt vector table. Interrupt vector table. So what is the purpose of having interrupt vector table? So interrupt vector table is used to store the addresses of 256 software interrupts in 8086. So obviously from type 0 to type FF, we are having 256 interrupts. Type 0 will start at 4 zeros and type 1 will have 0004, because to store IP it is required 2 memory locations, because IP instruction pointer in 8086 is a 16-bit and CS code segment is also of 16-bit. So 2 memory locations will need to access IP, and 2 memory locations need to have to store the CS register. Out of this, one interrupt is required to store one interrupt addresses. IP and CS need to require 4 memory locations. That's why the second interrupt type will always start from 0004. Further up to 256 locations it will be stored. So how many memory locations it need to have? From 4 zeros to 03FF. These many memory locations need to be there to store 256 IP and CS addresses. Okay, coming to the interrupt vector table. As I already told you, interrupt vector table is the table which stores the CS and IP values of each interrupt procedure. Here that is, interrupt structure of 8086 will be first kilobyte of memory from 4 zeros to 003FF locations. The vector table will be stored to store CS and IP values. So these 256 interrupt service routines will be addressed by using the interrupt vector table. This is the interrupt vector table of 8086, starting from the location 4 zeros, and the next will always be addressed by 4 other locations. So one interrupt, to access one interrupt, it is necessary to have 4 memory locations. So coming to the allocation of vector table, here the first type 0 interrupt is divided by 0. So if any number, you can take any number divided by 0. Can we divide any number with 0? Okay, you can tell that it is infinite. So we can't show the infinite in the 8086. We can't be, there should be the finite value. There is one error. That error is type 0 error in 8086. Type 1 is single step execution. Type 2 is non-maskable interrupt, as I already told you, NMI, non-maskable interrupts. As I already told you that for non-maskable interrupt, vector service routine address will be 0008H. If you remember in the previous slide, I have already mentioned that it will be the having 0008H. So next one is breakpoint interrupt. Up to type 27 up to type 31, these interrupts are reserved, but from 32 to 255 interrupts, these are available for further processes. This is the vector table which will be stored in the first kilobyte memory of 1 MB supported by 8086 microprocessor. So next, coming to the interrupt service routine. So what is the interrupt service routine? How the microprocessor will address the interrupt while executing the main program. Let us consider this is the main program. Okay. So main program starts here. The instruction, if we consider instruction N, next instruction will be N plus 1. So on, halt. Main program will be halted here. Somewhere around in the memory, we are having the interrupt program. Suppose if while the microprocessor is executing an interrupt and one interrupt occurred. Interrupt like type 26 interrupt has occurred while executing the instruction and 26 interrupt will be occurred while executing the nth instruction. What will microprocessor do? So as I already told you that if any instruction occurred in the instruction while executing the main program, that particular microprocessor executes the instruction and it will go to access the type interrupt. So type 26 interrupt is there. So where we will get the address of type 26? It will go to the vector table and it will fetch the IP and CS addresses and it will go to that particular interrupt routine. So here type 2, type 26 interrupts will be there. Instruction will be there. Some instructions will be there and at last it should have I return instruction. So after completing the execution of nth interrupt, it will go to the instruction execution. So after it will fetch the I return, it will return to the next interrupt, next line in the main program. Then it will continue execution of the main program until completion of program, or after some instructions when it encounters the other interrupt, the same instruction service routine will be happened. This is the interrupt service routine. So while executing one instruction in the main program, if processor encounters an interrupt, it will go to that particular interrupt service routine and it will execute the interrupt program until unless it has seen the I return interrupt instruction. So when it encounters the I return instruction, it will get back to the next line in the main program and it will continue the execution of the program. So this is all about interrupts and interrupt vector table and interrupt service routine. Until now we have discussed what are the interrupts present in the 8086, how interrupts will be accessed by the 8086, how many types of interrupts are there, what is the interrupt vector table, and how interrupt service routine ISR interrupt service routine is there in the 8086 microprocessor. Thank you.